Well, good morning, everyone. I hope everyone's got a lot of energy now, had a coffee break. I see the energy is flowing in the room right now. My name's Dustin Burson. I'm a software engineer at Microsoft, and I'm a part of the Health, Cloud, and Data group. And for the past year or so, I had the opportunity to focus on developing for the Internet of Medical Things, specifically devices. And reason why I'm here to talk today is to go over the IoMT FHIR connector for Azure. It's available on GitHub. We released it this past Monday, and I'm super excited for it to be out in open source currently. Open source is very important to us. It's a way for us to get additional feedback of what we're building and really engage with the community. So I'd encourage you to go check it out and provide feedback. And to kick things off, I'm going to start with a little bit of a demonstration. But first, I'd like to get a assessment of the room. So who here has a wearable or some kind of device that they wear day to day? So I myself have my Fitbit currently, and I'm also wearing another device here on my arm. This particular device samples at very high frequency. Right now it's set to sample every second. And it captures various biometric data points. For purposes of this demo, it's capturing my heart rate. And right now it's sending it up through the connector into a FHIR server. So I'm going to pull up Postman real quick, and I'm going to do GET request on my observation that's being filled out right now for the current hour. You can see here down below, it's a little small, but we have an observation that we started. And here is the value sample data type. If you're not familiar with this for use in observations, don't worry, I'm going to go into it later. And we're going to go ahead and refresh, and we'll be able to see that there's going to be a lot more values here filled in since we're 15 minutes past the hour since I last queried this. And we'll circle back later towards the end of the presentation, and we'll see how the values get filled out. But in addition, I set up a nice little Power BI dashboard that kind of splits the stream and is streaming my heart rate pretty much in real time. What you're seeing here is my max heart rate over 10-second windows. And I guess anyone can guess when the presentation kind of started? So we can kind of check back in a little later too to see if I get a little leveled out. But switching back, go over the session outline. So what I did do is kind of define what is IoMT, or the Internet of Medical Things, cover some key scenarios. Why is it important? And then kind of take you through our journey as our team has kind of gone through and evaluated this space and kind of what we thought was important when we were building for IoMT, some of the challenges we've encountered, and the lessons we've learned along the way. And then, I briefly brought up that example of the observation in FHIR with the sample data type. I'm going to go in that a little more details for those that may not be familiar with it, because that's really what we're using to represent the high-frequency data sets that we're capturing. And then following that, I'm going to kind of go in a little more detail what the connector does, what it's about, some of the high-level architecture components and how it gets configured. And then hopefully, if there's time, go through some places where we see kind of future improvements that can be made, specifically around the FHIR specification for supporting high-frequency data types, and kind of start a dialogue and get some feedback. So, to begin, what is IoMT? Well, you've heard me say that a couple times already, the Internet of Medical Things. So you consider a subset of IoT devices, or the Internet of Things devices, that are kind of pervasive now. They're everywhere. We have smart fridges, smart thermostats, smart doorbells. Well, you can think of this subset as being kind of a special case because it has patient health data. And they can run a gamut of different shapes and sizes. Some of them are worn, like the two I have on me today. There's other types of sensors that are ambient, so they live in the environment. So as people walk by, they can take some biometric readings like heart rate, respiratory rate, stress levels, and things like that. And then there's classes that are used. So you can have like injectables or inhalers, so like asthma inhalers or insulin pens and things like that. So what would you use this for? So there's a couple key scenarios. One of them would be patient monitoring, which in of itself can mean many different things. So you can have remote monitoring of your patients, particularly important for like home care or telemedicine. And it gives us an opportunity to kind of extend the reach of the clinic and keep tabs on patients, make sure they're doing well, and potentially intervene before adverse events occur or severity escalates. Then there's applications in the inpatient environment as well. Currently, there's a whole host of machines collecting data in inpatient settings, but a lot of that is kind of dying on the vine, if you will. It's not actually being egressed out, especially at the high sample rates that are being taken today. And there's an opportunity for that data set to be meaningfully used in various applications. There's a whole host of applications within research. So what signals are important? If I have biometric information and I can combine that with some clinical data, can I make inferences about that? One of the things that we're hoping to do with the solution is kind of empower those scenarios. And lastly, there's applications in smart hospitals. So why are we releasing an IoMT solution? First off, we kind of want to simplify the process of getting IoMT data in for physicians and researchers to use. And this we feel is going to promote and bootstrap the process of experimentation and learning, specifically, around what are good applications for this data. There's a lot of promising research starting already, but I think it's vastly untapped, and there's a lot of potential. And lastly, support and evangelize FHIR. So by providing this data stream that can easily ingress data into FHIR, we're kind of seeding the data ecosystem, if you will, and allowing other clinical data sets within FHIR to kind of combine and be used. So what are some things that we were looking for when we were building for IoMT? So one of the key points is we wanted to be able to handle the high frequency, high fidelity data sets. There's a lot of scenarios where you may have a few measurements a day, and those are important, and they have broad applications. So like someone post-surgical, goes in and they have to weigh themselves to see how their weight's progressing, and an increase in weight may introduce or indicate a complication. But there's other applications where you can have basically biometric data continuously streaming, and that can have power to add real insights into certain situations. So we really wanted to have a system that can scale and capture those data sets. Yeah. Also, if you want to be able to intervene or take action, the data has to be fairly low latency. So it doesn't do any good if you're capturing these high fidelity data sets, but you don't actually see them in your system of record for, say, 24 hours. That really doesn't do any good. We want to be able to associate the data to the patient. We have to have that clinical context, but do it in a safe and secure way. We also want to be able to support a multitude of devices, not being locked into one specific scheme or vendor or one format. And we also want to be interoperable, which is why we're looking to ingress this data set into FHIR. We're really wanting to make sure that the pipeline is private and secure, and was suitable for support and data analytics and machine learning modeling. So what are some of the challenges that we encountered, and if you were going to do this yourself, that you might encounter? So one of them would be late arriving data. So especially in the remote care setting, you're going to have a gateway or something that's streaming the data from the device. Your connectivity is not always guaranteed. So it's a different setting if you have like an EKG or some other system like an inpatient hospital where you can be guaranteed that on regular intervals, data is going to be streaming. But in the remote setting, you may or may not have connection. It may go in and out. So you have to handle when data that was supposed to be there an hour ago is now just arriving. Similar to that is out of order data. You may not have control over the order in which the data that is late is arriving. The device could be buffering the data and then send you the latest data, but then start backfilling some of the history. Given the scenario of like losing connectivity, you also have to handle duplicates. So if the device is sending, or the gateway is sending data into the cloud, and your connection drops, the device, if it doesn't get the acknowledgement that that you've received that data packet, it might send it up again, and it should. Well, on your end, you might have actually started processing that, and you've successfully committed it as a record. But what you don't want to have happen is when the device sends it again because it didn't get the acknowledgement the first time, that you don't duplicate the data set. Linking the data to the patient, the devices themselves rarely have actual patient data on them, and for good reason. So you still want to be able to link the data once it's ingested into the cloud to the correct patient, so it flows into their record. There's also this interesting tension point of balancing the latency of the data that you're collecting and the load on your FHIR server. The FHIR server that we're loading data to is ideally not just for the IoMT data streams. It's serving other workloads in a clinical setting. Lastly, many devices represent data sets completely differently. And it's a challenge to have a solution that should be able to accommodate all of them. And one other challenge with especially around the high frequency data sets, is keeping the number of resources that you're generating reasonable, which kind of segues into some of the lessons learned as we were kind of building out this pipeline. So one, especially when you're dealing with high frequency data sets, a single value observation is not sufficient. So if you're sampling out once a second, you can see how that is going. If you're creating single value observations, you're going to really flood the medical record with observations quickly. And even if your FHIR server can keep up with and curating those records, it's a pain to consume them on the back end. Another lesson learned is collecting data on devices presents problems. So anytime you are putting like this logic of like, this is how I want to group the data, this is when I want to flush the data out, that adds additional complexity to the device. And it can also introduce latency. So if your device or your gateway is what's in control of how often data is getting sent to the cloud, like it's doing some buffering, it's doing some conversion, those are time periods that you don't have to actually reason over that data set. And there's also a problem around code portability. So it's one thing if you do like this gateway or like code for a device that's sending data to the cloud, and you have like this robust implementation that handles how you want to buffer the data and send the data up and maybe convert it to FHIR and stuff. But how you're going to really make that portable across the whole suite of devices. And lastly, FHIR on devices can be hard. The FHIR spec is evolving. So if you have devices that have a specific implementation of FHIR and they're doing devices natively on the device, but you want to then update them to support a later version of FHIR, you may not necessarily have control of when that update's going to occur, and then you have to then account for different versions of FHIR out in the wild. And the FHIR payloads themselves can be quite large compared to what these devices are normally used to sending. So it's not necessarily the most efficient way of egressing these data sets, especially when they're high frequency into the cloud. So I'm going to go into an example of how we store the high frequency data sets. So right now we're using the sample data type in the observation. So the key part is you have a sequence of values, and you define a period in milliseconds. So here's the sequence of values. It's a 10 character or 10 length array, and we have multiple readings. But you can see here in the middle we have some missing data, which are represented by E or error. There's a couple other components about this data type, like you can support multiple dimensions and things like that. We're not using those in our current implementation, so any of the examples we see today will have a dimension of 1. But yeah, so this is how you would show a large period of data. So that brings me to the IoMT FHIR connector for Azure. So we group things up into 4 distinct steps and how we process the data that's coming in. So first we normalize. So on ingest, we interrogate the payloads and we extract values, and we see what do we know, and we put them into an intermediate format. Still not FHIR, but it serves as a pre-step for the next processing, in which we group. So we take these data sets, these normalized data sets, and we group them by the type of device, type, so whether it's a heart rate, a blood pressure, and so on, and a time window. And then we transform. So this we take the grouped normalized data models, and we transform them into FHIR observations. And this is also where we do things like linking to the patient, and so on. And then we persist. So we persist the observations in a FHIR server. So what are some of the key benefits of the connector? One is scalability. So by being built on Azure and the components underpinning it, you can kind of scale up and down to meet your demands. So you can go with the lowest level if you don't have a lot of high frequency data sets, or you have just a few devices, a couple hundred, or if you're running a large hospital or a large organization with thousands upon thousands of connected patients. You can scale up to meet your needs. Next is interoperability. With the data landing in FHIR, you have an interoperable data store of IoMT data to use in your clinical workflows. And cost and time savings. So, there's nothing particularly novel about what we built. They're all off-the-shelf Azure services and the code that runs on them. Anyone can go out there and kind of spin it up, but we have the project available in open source, so you don't have to do that work, and you can kind of go deploy it and then extend it for your own particular use case. And lastly, kind of underpinning all of this is security and compliance. So the connector has been designed for HIPAA, high trust, and GDPR, specifically with all the Azure services that we're using, meeting those barriers. And a couple more bullet points. The end-to-end latency is configurable by you, so you have direct control over essentially the buffer time between when data is ingressed and when it gets flushed out to your FHIR server. So you can have something, say, 30 seconds, 5 minutes, or an hour. It's really up to you and your particular use case. So you can control that balance. But just so you know, even though we're buffering it, the time period that is being configured, none of the data is lost. So that 1 second sample rate, that data is being collected. And it'll eventually make it into your FHIR server based off of your end-to-end latency configuration. Another thing is it seamlessly connects to the Azure IoT suite of services like IoT Hub and IoT Central. So if you need those for your device management, device updates, and things like that, you can easily connect it in and flow your data streams. We also designed it in mind for being extensible for analytics. So if you think back to the demo I started out with, that's being achieved by essentially forking the data stream and doing a stream analytics job that is doing a nice little max of my heart rate over a 10-second period and flushing it into Power BI, while it's simultaneously going into FHIR. What are some of the requirements to use the connector? Right now, we're supporting R4 FHIR servers with, as new versions of the standard come online, we'll support those as well going forward. Your FHIR server needs to support OAuth 2.0 and have an existing device resource and patient resource on the FHIR server. So this is how we, by default, do the patient mapping, is we assume that you've already set up a device with an identifier and a patient resource that's linked to that device. An identifier is essentially what's coming in the IoMT payload, and we do the lookup and association for you. We really wanted to be, as we were looking into this space and kind of working with partners, we were finding that the specific workflow of how patient and device linking occurs was very specific to a lot of workflows, and there wasn't like a one-size-fits-all solution. So we didn't really want to implement anything specific around that. And lastly, the normalization and FHIR mapping require, there's a template for each that you'd have to set up to kind of map your device data as it comes in. So not covered, kind of went over this briefly in the last slide, but we're not doing any device security or device management. Those are covered by other products like IoT Central, IoT Hub, or other third-party providers. So we're not really looking at stepping into those areas. We view ourselves as something that can connect seamlessly to those services from their data endpoints. And as I mentioned, the device provisioning and patient provisioning in the FHIR server is something that we don't really cover. So what exactly happens during the normalization step? So it kind of breaks down into two things. We match and extract. So the current out-of-the-box implementation is using JSON path for the templates. And what happens as messages are pumping in, we evaluate the templates. If we find a match on one or more templates, then we extract the values that are mapped in that template. So you can see on this example, we have 3 different devices. They're all representing heart rate in a slightly different way. And then on the output, we have a common normalized model. This is a simplified version of what's going on, but it kind of gives you an idea of what's happening. And then lastly, one of the things that we do is a projection. So on the next slide, I have an example of really what that looks like. So it's fairly common in devices where they'll send a payload where you'll have multiple measurements of different types in a single payload. So one of the things that we'll do for you is if you, with the templates, you'll set up 3 templates to look for each of these, and we'll extract and parse that one message into 3 in this case. So we had one message that had a heart rate steps and heart rate variability, and now we've kind of split it out into 3 where we have an individual heart rate steps in HRV. And then those can go on to be separate observations created in FHIR. Here's a quick example of a template. So on the gray shaded area is an example of like a very simple message payload that might be coming in. So we have a JSON payload, and we have a body element, and then we have properties with heart rate, date, and device ID. On the template, we give the template like a type name. So that's going to be our common type that is used later down when we do our FHIR mapping. And then the first thing we have is a type match expression. So this is what gets evaluated by the normalizer. And if we get a match for this, essentially, if we find a J token or J tokens that match this JSON path expression, then we know we have a match. And then we can go on and extract values. So here we have the JSON path to extract the device ID. And then if we go over and look at some other parameters of the template, we have a JSON path to extract the timestamp for the measurement that occurred. And then we have an array of extraction and types for values that we want to associate. So here we have, we're pulling out the heart rate and giving it a value. So moving on to the grouping and buffering stage. It leverages stream analytics. So stream analytics, for those that are not aware, is kind of a stream processing query service. So it allows you to essentially do SQL-like queries on top of temporal strings, or temporal streams of data. So you basically give it a time window that you want to operate on, and you can do SQL-like queries on those. Mentioned earlier that this controls your end-to-end latency, so how often data is being egressed to your FHIR server. The job itself is partitioned by device ID, so we get some nice parallelization across. And just as a kind of a note, so as we're ingesting data, our ingestion endpoint is an Azure Event Hub, and as that scales up and down to meet your messaging demands, you'd also want to scale up or down your stream analytics job that underpins the service. Next phase is the FHIR conversion. So there's a couple different things going on here. There's some things that you define, and then there's other things that the system implicitly does for you. So some of the things that you would define is the period of the observation. So do you want to create a 1 hour observation, a 1 day observation, or a single instance? So in the example that I started with, I'm creating 1 hour observations. So as I'm streaming data every hour on the hour, as data is coming in, a new observation will be created and then continue to be filled. You define the codings that you want to associate with your data as it's streaming in. So you define your codable concepts. And in this case, I have a link code for heart rate. You set your data type. So the most common data type that we're using right now is sample data, but there's other data types, value quantity, codable concepts, and things like that you can also leverage as well. Those would be more for not necessarily high frequency data, but events and so forth. The pipeline can be used for those as well. We take care of mapping data, so all the individual data that the device would be sending up, we take care of aligning that to the correct observation, generating the identifier, linking the patient and device with the observation. So as data is coming in, we'll interrogate that device ID, look up the appropriate device based off the identifier, and then look up the patient and know what to associate with the observation that we're creating. Additionally, we also support components. So if you have the observations that have multiple values, we can fill those out in the components in the mapping as well. And here's just an expanded version of the template, just to get an idea. And lastly is persistence. So all the data that flows through the data connector is transitory. So there's no additional persistence other than the configured FHIR server that you provide. So how do you get started? Well, first, like you clone the repository. In the repository, we have 2 ARM templates, or Azure Resource Management templates, that essentially spin up everything for you on your Azure subscription. You just go in, enter in some configuration parameters, provide your OAuth connection details for your FHIR server, and hit deploy. It takes about 10 minutes, and you'll be up and running. In addition to we also have another ARM template that provides essentially a sandbox environment. So in addition to the connector, it will spin up a FHIR server, the Azure API for FHIR, and an IoT Central instance. And one of the nice things about the IoT Central instance is they also support what are simulated devices. So essentially the sandbox comes spun up with 2 different devices that are simulating data ready to go, and kind of can give you an idea of what it would look like to play with. And then lastly is uploading the configuration/mapping files. So that's where you would say, how you want your device data to be mapped into FHIR. So what are some things that we can improve? One of them is looking at limiting history creation. So one problem that we have currently is as we decrease the buffer window that we're buffering data and egressing it into FHIR, if your FHIR server supports creating history records, well, essentially every time we're appending to that record, we're creating a new history version. So one thought that we've had and we've been toying around with is kind of looking at a special operation that we can add to the observation resource. And this might be some of the things we consider how it may work. So one of them would be, the requirement is you could append to the observation while it's in the preliminary status. And while it's in the preliminary status and you're using this operation, new history records wouldn't be created. So this will kind of allow you to hydrate out the data stream as time goes on. And then once you're at a point in time where you're essentially wanting to done or seal the data stream and say that this observation is final, then from that point on, the observations in the final status, history would be maintained normally. And another problem that we are looking at and how we can improve is kind of sparse data streams. So especially we find this is a problem a lot in the wearable space and the consumer space, where the sample rate on devices is variable. And the sample data type works great for things like the EKG, where you're guaranteed to essentially get measurements, at a certain frequency for the sample period. But devices like the Apple Watch, where normal mode of operation is measurement like every few minutes, but if you put it into exercise mode, you're sampling every 5 seconds. So that kind of puts you in a little bit of a problem with the current way the data is represented. If you don't want to lose any data, then you have to set your period on the sample data type sufficient so you can support that high frequency data set. But what happens then is when you're in the non-exercise mode in the Apple Watch case, you're essentially have a lot of E's or empty values within the stream that you kind of still have to parse through. And it's not necessarily the most efficient way to represent the data set. So one thought is essentially adding a new set or extending it such that we include a time dimension, which we can indicate just the values that occurred, and then basically the milliseconds or some other time component that they occurred within the observation. And this would allow you to represent these sparse or variable data sets without worrying about any loss in accuracy. So in summary, we kind of went over and defined IoMT. We covered our challenges and lessons learned. And we did an overview of the IoMT FHIR connector for Azure. And kind of went over some potential places where we could improve. And just out of curiosity, we're going to see how I'm doing here. I don't think it's refreshed. I'm going to do, the little widgets sometimes don't update when you don't have focus. Oh, it looks like it's still up there. And then real quick, we'll switch back into Postman. So you can see here that we got a lot of empty values, and when we refresh, we got a lot more data now. So I'd like to thank you for attending the presentation. I encourage you to start the repository. Please contribute to the project, and if you'd like to learn more or have questions, feel free to see us after. Okay, or take questions now as well. Yes? So the question was, are we creating multiple observations or appending to a single observation? The answer is it's a bit of both. So, so I think the default implementation would be you're creating that observation once an hour. So while the data that aligns to that hour would be appended or inserted depending on, because if the data arrives out of order, it might not necessarily be appended to the stream, it might be inserted into the middle of the value sample data type. But so yeah, it's a bit of both. But as data arrives that falls into other hour buckets, or if you set up like a day length observation, other days, new observations would be created and filled based off of which, the time periods that those data points slot in.
So during that 1 hour period, all those data you collected in the connector just cached in the connector pipeline and you flush the observation?
So the question is during that 1 hour, is all that cached in the connector pipeline? No. So the hour observation time is separate from the caching or the buffering time. So you can set it to be, say, like 5 minutes. So that's how often data is going to be flushed into FHIR. So essentially, what's happening in the demo that I have up here that I was kind of showing is I have the buffer set for 30 seconds. So what's happening is every 30 seconds, the data is being collected, and then it's flushed and appended into the FHIR observation. Yep. Oh, sorry.
You talked a little bit about maybe some new FHIR operations that would make it easier to put data into one of these long-term observations.
Yeah.
And a little bit about data representation inside of FHIR to do better with sparse data. What about on the other side for working with data that are stored in these kinds of hour-long observations with lots of sample data? Are there operations that would make it easier for clients to do common tasks with that kind of sample data?
Yeah. Oh, that's a great question. So the question is how do you consume these value sample data types? And I think that's a great observation and a great question. And that's one of the other things that we were thinking of would be potentially a good place for like an operation or something along those lines, because it's kind of unwieldy, especially if you have to stitch together multiple observations. And like one of the common ways of dealing with this data would be in a tabular format, which isn't kind of represented here. So traditionally, you'd want to take that data stream out and then also correlate it with all the time values that align with it, so you know exactly when each measurement occurred. So I could see definitely a case for having an operation where you kind of append it to an observation search query that's looking for a specific code of some kind, and then the expectation is it would kind of project out into a tabular format all the observation, like the dates and the values for the value and any subsequent components. But also interesting to see what other people are thinking, what would be useful. Yeah, thank you. Oh, yes. So the question was how, like the late arriving and out of order problem. So the two ways. One, the late arriving data is kind of handled for us by Stream Analytics. So like in that buffering window, it tries to group by the timestamp that we set. And the expectation is as data is streaming in, it should conform with those. But essentially what happens if there's data that arrives that's late, it gets put into the current time bucket. And then on the FHIR conversion side, we take care of splitting that out. So we recognize, oh, you configured this observation to be generated once an hour. Based off these time values, we're seeing, well, there's like actually 5 hours worth of data here, and they align to these observations. And then the out of order is like as the data is coming in, we don't assume the order. We just assume like this is the group of data that's coming in for this hour, and then we sort it as it comes in, and then if it's already been merged with the observation, we basically reconstruct the the components of the time and the values, and we basically figure out where things slot, and we insert them into the correct place in the observation or observations if that's appropriate. Yeah. Sorry, is there any other questions? Oh, sorry.
Do you support mapping into FHIR profiles, such that maybe map the data into the personal health devices profile?
So We don't have anything that explicitly supports like requirements on specific profiles at this point in time. But that was actually one of the things that we're looking at implementing, and it could be extended with the current implementation as it stands now. Yeah. Yeah. Thank you. Cool. Sorry, what was the question? So historical analysis? Well, we're storing it in FHIR for historical analysis. The question was where would we prefer? That's really the implementation. So the question is would it be Cosmos DB? That's an implementation detail of your specific FHIR server. If you're using the Azure API for FHIR, it'd be on the back end underpinned by Cosmos DB. If you're using the open source, you'd have the choice of using Cosmos DB or a SQL server. But yeah. Yes. Sure. So the question was like, how does like the buckets work? And that's kind of really more of like how you evaluate the value sample data type. So if you think back in the value sample data type, there's the string of values. And what I left off there, that's part of the observation, is like the effective period. So we're giving a period, in this case, we're using an hour of the start and the end. And then the sample data type itself has a period. So you essentially, you start with value 1 or index 0, and that's time 0 within the offset of the start of the period. And you essentially just increment the period from that forward, so that slots your... Yes, yeah. Yeah, so that's kind of going back like to the sparse, like if you have a sparse data type where you kind of want to set it to a second because your device may sample at once a second, but it doesn't always sample at once a second. It may not be necessarily the best way to represent it, but this is kind of the current data types we have to work with. But okay, great. Cool. Okay. Well, thank you very much, everyone.